Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual currents of the 19th century, particularly within British academia, presented a landscape both fertile for discovery and marked by considerable constraint. It was within this milieu that Joseph Sylvester emerged, a figure whose prodigious mathematical talent would eventually reshape fields of study. Yet his early journey was profoundly influenced by the societal and religious barriers of his time. Born in London in 1814, Sylvester's early life unfolded against a backdrop where opportunities for individuals of Jewish heritage were severely restricted. The prevailing test acts, though gradually eroding, still cast a long shadow over access to the established institutions of higher learning, including the ancient universities of Oxford and Cambridge. These represented a pervasive cultural and intellectual segregation that could stifle even the most brilliant minds. Sylvester's initial education was a testament to his family's commitment to his intellectual development, availing him of private tutors and schools that could provide a rigorous grounding in the classics and the nascent sciences. From an early age, the intricate patterns and logical structures of mathematics captivated him. An anecdote often recounted speaks of his precocious engagement with arithmetic, a fascination that quickly escalated to more abstract realms. The intensity of his developing passion is undeniable. It was a passion that transcended mere academic exercise, offering a sanctuary of order and beauty in a world that often seemed resistant to his full participation. The path to Cambridge, specifically St. John's College, which he entered in 1831, was a significant undertaking, requiring a special dispensation due to his Jewish faith. This admission itself was an act of defiance against the prevailing exclusionary norms, a crack in the edifice of tradition that allowed a singular talent to flourish. At Cambridge, Sylvester encountered a curriculum steeped in the Newtonian tradition, with a strong emphasis on pure mathematics, particularly mechanics and the calculus of variations. The intellectual environment was rigorous, demanding, and competitive, a crucible in which nascent mathematical abilities were tested and refined. The challenges, however, extended beyond the academic. St. John's College offered greater flexibility compared to certain other institutions, yet the wider university framework presented constraints. A requirement for degree conferral involved subscribing to the 39 Articles of the Church of England, a condition Sylvester found impossible to meet. Consequently, despite his academic excellence, including achieving second wrangler in the 1837 mathematical tripos examination, a notable accomplishment placing him among the year's leading mathematicians, he could not formally graduate. This situation presented a significant irony. He was recognized for his mathematical skill by examiners and colleagues, yet denied the formal acknowledgement that would have greatly aided his professional advancement. This Cambridge period proved influential, exposing Sylvester to contemporary advanced mathematical concepts, including the contributions of continental mathematicians such as Lagrange, Laplace, and Poisson, whose work would profoundly shape his future endeavors. He assimilated these ideas with immense eagerness, commencing the development of his unique methodology for tackling mathematical challenges. His initial contributions, prior to their most impactful published forms, already showcased exceptional originality and a profound grasp of the fundamental structures within mathematical relationships. British mathematical pursuits of that era frequently centered on applying calculus to physical phenomena and advancing analytical mechanics. While Sylvester excelled in these domains, his intellectual focus extended to more profound, abstract inquiries, foreshadowing his future theoretical innovations. The absence of the Cambridge degree limited Sylvester's early professional opportunities. Without this formal credential, academic posts and professions requiring university qualifications remained largely out of reach. This led him to accept positions that, while intellectually engaging, did not always align with cutting-edge mathematical research. He worked as a private tutor, a capacity that refined his comprehension of mathematical principles through teaching, and he also undertook actuarial work, a field offering practical applications for his mathematical expertise. These experiences, though perhaps falling short of the academic recognition he merited, provided him with a comprehensive understanding of mathematics' utility and sharpened his analytical acumen. The societal environment in mid-19th century Britain was a multifaceted blend of advancement and bias. While scientific societies were becoming more inclusive and intellectual discourse was expanding, the legacy of religious discrimination persisted. For Sylvester, this meant his early career involved constant negotiation with these limitations. He published his initial mathematical papers in various journals, but without the institutional backing and widespread recognition afforded by a university position. His voice, though brilliant, struggled to achieve the prominence it warranted. The intellectual world of Britain at this time was largely dominated by figures associated with the established church and universities, and breaking into this inner circle required overcoming significant cultural inertia. Despite these impediments, Sylvester's intellectual fire remained undimmed. His mind was a forge, constantly working on problems that were both abstract and profound. He possessed an almost unparalleled ability to perceive the underlying symmetries and algebraic structures within seemingly disparate mathematical objects. This innate gift, combined with his rigorous training, set him apart. The challenges he faced in his early career served, in a peculiar way, to sharpen his focus, compelling him to rely solely on the power of his intellect and the elegance of his mathematical reasoning. His early years were thus a period of intense personal intellectual development, a gestation of the groundbreaking ideas that would later define his legacy. Even as the external world presented a more formidable set of obstacles, the stage was being set for a remarkable career, one that would contribute immensely to mathematics and serve as a testament to the resilience of human intellect against societal constraints. His journey was a quiet, determined ascent, driven by an internal compass pointing resolutely towards the frontiers of mathematical understanding. The intellectual landscape of the mid-19th century presented a fertile ground for abstraction, a period where the very essence of mathematical structure began to be explored with unprecedented depth. Within this vibrant milieu, James Joseph Sylvester emerged as a pivotal figure, particularly through his foundational work in invariant theory. This burgeoning field sought to understand the properties of algebraic expressions that remained unchanged under certain transformations, a quest that promised to illuminate the fundamental nature of algebraic forms. The challenge was profound: how to systematically identify and characterize these unchanging quantities, the invariants, and their related counterparts, the covariants, as algebraic expressions themselves transformed. Sylvester approached this challenge with a combination of insight and systematic strength. He recognized that the solution required creating a new system, a symbolic calculus, designed to manage these transformations and their impact on algebraic expressions. His initial publications concerning invariant theory, particularly those from the late 1840s and late 1850s, established a foundation for this entire field. He introduced a potent notation utilizing symbolic operators, enabling him to represent the process of identifying invariants with exceptional brevity and grace. Consider a general quadratic expression in two variables, such as a times x squared plus b times x times y plus c times y squared. The objective was to determine a quantity derived from its coefficients, a, b, and c, that preserved its value even when the variables x and y were substituted with new variables, x and y, linked to x and y through a linear transformation. This constant quantity is an invariant. Sylvester's brilliance manifested in his capacity to broaden this concept. He did more than identify invariants for particular forms. He formulated a complete framework for their systematic creation. His advancement of the theory of symbolic operators, frequently called the symbolic method, served as a potent instrument for this discovery. He conceptualized operators that acted upon algebraic forms, and by examining the behavior of these operators under transformations, he could isolate the expressions that remained invariant. This process resembled deciphering a hidden code that unveiled the inherent symmetries within algebraic structures. For example, he utilized operators representing differentiation with respect to the coefficients of an algebraic form, and by applying these operators in particular sequences, he could derive the invariants and covariants. A vital concept he introduced was the syzygy. Within invariant theory, syzygies represent relationships among invariants and covariants. Sylvester understood that the complete set of invariants and covariants for a given algebraic form was structured internally, governed by these fundamental connections. Understanding these syzygies was essential for a complete description of the invariant system. It meant that an infinite number of these quantities were unnecessary. A finite set of generators, along with the syzygies connecting them, sufficed to describe the entire structure. This was a profound insight, providing a pathway towards a complete and organized understanding of algebraic forms. The problems Sylvester addressed were central to the mathematical concerns of his era. Mathematicians were grappling with the classification of geometric objects described by algebraic equations and the understanding of how these descriptions changed under various geometric transformations. Invariant theory provided the essential tools for this endeavor. For example, in geometry, the shape of an ellipse is described by a quadratic form. If one rotates or translates the coordinate system, the coefficients of the quadratic form change, but the ellipse itself remains the same. The invariant associated with this quadratic form would be a quantity that stays constant throughout these transformations, capturing the intrinsic properties of the ellipse, independent of its orientation or position in the coordinate plane. Sylvester's work provided the systematic machinery to find these intrinsic properties for a vast array of algebraic expressions. His approach was highly original. Prior to Sylvester, mathematicians often relied on ad hoc methods to find invariants for specific cases. Sylvester, however, provided a unifying framework. His symbolic method was a sophisticated algebraic machinery that could be applied to any homogeneous polynomial in any number of variables. This systematic approach was a significant leap forward, transforming invariant theory from a collection of specific results into a coherent and powerful branch of mathematics. The elegance of his notation and the depth of his conceptual framework meant that his work resonated deeply with mathematicians across Europe. The impact of Sylvester's work on invariant theory is immeasurable. He is widely credited with founding the field, establishing its core concepts, notations, and methods. His symbolic notation provided the initial impetus. The concepts of invariants and covariants, as elucidated by Sylvester, became fundamental tools in algebraic geometry, the study of geometric shapes defined by algebraic equations. They allowed mathematicians to classify geometric objects based on properties that were independent of the chosen coordinate system. Furthermore, the theoretical underpinnings of invariant theory, as developed by Sylvester, have found profound resonance in modern mathematics and physics. In algebraic geometry, the study of moduli spaces, which parameterize families of geometric objects, relies heavily on invariant theoretic concepts. In theoretical physics, particularly in areas like quantum field theory and string theory, symmetries play a paramount role. Invariant theory provides a powerful mathematical language to describe these symmetries and their consequences. The search for fundamental laws of nature often involves identifying quantities that are invariant under certain physical transformations, a direct descendant of the problems Sylvester first systematically addressed. Even in computer science, particularly in areas like computer graphics and machine learning, the principles of invariant representation are employed to ensure that algorithms are robust to changes in input, orientation, or scale. Sylvester's exploration of syzygies, the relations between invariants, also foreshadowed later developments in abstract algebra, particularly in the theory of modules and commutative algebra. The idea of a finite set of generators and relations to describe a complex algebraic structure is a recurring theme in modern algebra. His work, therefore, served as a crucial stepping stone for the broader development of abstract algebraic thinking. He provided a rigorous and systematic way to understand the intrinsic properties of algebraic forms, a pursuit that continues to drive mathematical discovery today. His early contributions to this field were the creation of a new mathematical universe, a testament to his singular vision and intellectual prowess. He offered a new lens through which to view the world of algebra, revealing a hidden order and a profound interconnectedness among algebraic expressions. The intellectual landscape of mathematics, particularly in the latter half of the 19th century, was profoundly shaped by confluence of abstract reasoning and burgeoning combinatorial inquiry. Following his foundational work on syzygies and invariant theory, where he illuminated the intricate relationships between algebraic forms and established a systematic approach to understanding their intrinsic properties, Sylvester's gaze turned toward the elegant and often deceptively simple world of numbers. His explorations in number theory, especially his profound engagement with partitions and Diophantine equations, reveal a mind adept at uncovering deep structures within seemingly elementary arithmetic. The problem of partitions, in its essence, asks for the number of distinct ways a positive integer can be expressed as a sum of positive integers. Consider the number 4. It can be represented as 4 or 3 plus 1 or 2 plus 2 or 2 plus 1 plus 1 or 1 plus 1 plus 1 plus 1. The order of the summands does not matter, therefore, 4 plus 1 is the same partition as 1 plus 4. This seemingly straightforward question quickly escalates in complexity. For instance, how many ways can the number 100 be written as a sum of positive integers? The sheer volume of possibilities necessitates a powerful analytical framework. Sylvester's approach to this combinatorial challenge was characteristically insightful. He embraced the power of generating functions, a technique that translates a combinatorial problem into the language of power series. For partitions, the generating function is a product of infinite series. The coefficient of x to the power of n and the expansion of this product precisely enumerates the number of partitions of n. Specifically, the generating function for partitions is given by the infinite product. The product from k equals 1 to infinity of 1 divided by the quantity 1 minus x to the power of k. This elegant expression encodes all the information about partitions. Expanding this product, term by term, allows mathematicians to extract the partition numbers. Sylvester developed novel combinatorial arguments and theorems that shed new light on the nature of partitions. One of his most celebrated contributions is the partition theorem, which relates partitions into distinct parts to partitions into odd parts. He demonstrated that the number of partitions of an integer into distinct positive integer summands is equal to the number of partitions of that same integer into odd positive integer summands. This theorem, a beautiful example of duality in combinatorics, was proven by Sylvester through intricate combinatorial reasoning and the manipulation of generating functions, revealing a hidden symmetry within the partition landscape. His work here provided a concrete illustration of how abstract algebraic tools could unlock profound truths about discrete mathematical objects. Sylvester's prowess extended to the realm of Diophantine equations, named after the ancient Greek mathematician Diophantus. These are polynomial equations for which only integer solutions are sought. A classic example that captivated mathematicians for centuries is Pell's equation of the form x squared minus d times y squared equals 1, where d is a non-square positive integer and one seeks integer values for x and y. The challenge lies in finding all integer solutions, especially for large values of d, where trivial solutions like x equals 1 and y equals 0 are readily apparent, but the fundamental solution, the smallest positive integer solution, can be elusive. Sylvester's engagement with Diophantine equations involved developing systematic methods for their analysis. He contributed to the understanding of the structure of their solution sets, building upon the work of mathematicians like Fermat and Lagrange. His investigations into these equations focused on uncovering the underlying algebraic principles that govern the existence and nature of integer solutions. He explored connections between these equations and continued fractions, a powerful tool for approximating irrational numbers and for solving Pell's equation. The continued fraction expansion of the square root of d provides a direct route to the fundamental solution of Pell's equation, a relationship Sylvester deeply explored. His work on Diophantine equations also extended to more general forms, including linear Diophantine equations in multiple variables and quadratic Diophantine equations. He sought to establish necessary and sufficient conditions for the existence of integer solutions and to develop algorithms for finding them. This pursuit of generality and algorithmic solvability marked a significant step in the development of number theory as a rigorous and systematic discipline. The techniques he employed often involved modular arithmetic and properties of divisibility, demonstrating a deep intuition for the arithmetic properties of integers. The enduring legacy of Sylvester's work in number theory is undeniable. The theory of partitions, which he so significantly advanced, remains a vibrant area of mathematical research with applications in fields ranging from statistical mechanics and quantum field theory to the analysis of algorithms in computer science. The enumeration of partitions is crucial for understanding the state space of certain physical systems and for analyzing the complexity of computational processes. His insights into the structure of solutions to Diophantine equations continue to inform contemporary research in analytic number theory and algebraic geometry. The elegance and power of the generating functions he wielded have become standard tools in the combinatorialist's arsenal, a testament to their profound utility and the foresight of their early proponents. His efforts to systematize the study of these number-theoretic problems laid the groundwork for future generations of mathematicians, solidifying his place as a pivotal figure in the development of modern number theory. He offered a new perspective on the inherent order within the integers, demonstrating that even the most elementary arithmetic concepts could yield profound mathematical exploration. Sylvester's intellectual odyssey, having illuminated the intricate landscapes of number theory and combinatorics, pursued further avenues of mathematical inquiry, extending his profound influence into the realm of linear algebra and matrix theory. The problems that occupied him in this domain often stemmed from the need to understand and solve systems of linear equations, a cornerstone of scientific and engineering disciplines. The challenges of characterizing the behavior of dynamic systems, particularly in control theory and the analysis of linear transformations, demanded more sophisticated tools than were readily available. A central contribution arising from this period of his work is the formalization and analysis of what is now recognized as the Sylvester equation. This fundamental linear matrix equation, expressed as x plus xb equals c, presents a significant problem in mathematics determining an unknown matrix X, given the known matrices A, B, and C. The equation's ubiquity arises from its appearance in a multitude of contexts. In control systems engineering, for instance, it emerges when analyzing the stability of linear time invariant systems, particularly in the design of controllers and observers. The solution to the Sylvester equation provides crucial information about the system's dynamics, such as its controllability and observability. Sylvester's unique approach to this problem involved a deep dive into the theoretical underpinnings of matrix operations and their properties, while explicit solution methods for the general Sylvester equation, such as the Boyle-Stewart algorithm, were developed later. Sylvester's foundational work laid the essential groundwork. He explored the conditions under which such an equation would possess a unique solution, or indeed any solution at all. His investigations into the properties of matrices, their eigenvalues, and their spectral properties provided the conceptual framework necessary for future advancements. He recognized that the solubility of x plus xb equals c was intimately linked to the spectral properties of matrices A and B, specifically whether they shared any common eigenvalues. This insight was profound, establishing a direct connection between the algebraic structure of the matrices and the existence of a solution. The modern relevance of the Sylvester equation is exceptionally high, underscoring its enduring significance. It remains a critical tool in numerous scientific and engineering fields. In computational science, efficient algorithms for solving the Sylvester equation are essential for simulations in fluid dynamics, structural analysis, and quantum mechanics. In signal processing, it plays a role in filter design and system identification. The equation's presence in areas like image processing and econometrics further testifies to its broad applicability. Its analytical properties continue to be explored with ongoing research into numerical stability, efficient solution techniques for large-scale systems, and generalizations to more complex matrix structures. The theory developed around this equation has become a cornerstone of modern linear systems theory, a field that underpins much of contemporary technological advancement. Sylvester's contributions to matrix theory extended beyond the singular equation. He was deeply involved in the early development of matrix algebra, exploring concepts such as matrix determinants, matrix inverses, and the theory of matrix invariants. His work on invariants, in particular, sought to identify quantities associated with a matrix that remained unchanged under certain transformations, a concept with deep roots in geometry and algebra. He recognized the potential of matrices as powerful algebraic objects in their own right, capable of representing transformations and encoding intricate mathematical relationships. This perspective was revolutionary, moving beyond matrices as mere arrays of numbers to viewing them as entities with their own rich algebraic structure and analytical properties. His exploration of these structures helped to elevate matrix theory from a specialized area to a fundamental branch of mathematics, influencing the development of abstract algebra and functional analysis. The rigorous analytical methods he applied to matrices provided a template for future mathematicians grappling with complex algebraic structures. His engagement with these theoretical constructs cemented his legacy as a pioneer in the formalization of modern mathematical tools. Sylvester's intellectual pursuits extended with remarkable vigor into the realm of geometry and trigonometry, areas where his characteristic blend of algebraic insight and geometrical intuition yielded significant advancements. The prevailing mathematical landscape of his era grappled with the challenge of articulating geometric truths with greater elegance and analytical power. Proving theorems often relied on intricate constructions and a sometimes cumbersome reliance on classical methods. Sylvester, ever the innovator, sought to infuse geometry with the precision and generality afforded by algebraic techniques, thereby forging new pathways for geometrical reasoning. One notable area of his engagement was synthetic geometry, a field concerned with proving geometric propositions through logical deduction and construction, often without recourse to coordinate systems. This approach emphasized purity of method, and Sylvester recognized opportunities for enhanced analytical rigor. He explored the properties of geometric figures, seeking to uncover underlying algebraic relationships that govern their behavior. His work often involved the creation of novel geometrical concepts and the development of specific notations to represent them, facilitating a more systematic study of geometrical properties. For instance, his investigations into the configurations of points and lines and the properties of curves often led him to formulate new theorems and proofs that were both insightful and algebraically transparent. He approached these problems with a keen eye for the fundamental structures that underpin geometric phenomena, aiming to reveal the algebraic skeleton within the visual form. His contributions to trigonometry also reflected this desire for clarity and advancement. Trigonometry, vital for navigation, astronomy, and surveying, was a field ripe for refinement. Sylvester sought to present its principles in a manner that was both comprehensive and accessible, developing methods that simplified complex calculations and offered deeper theoretical understanding. He explored the relationships between trigonometric functions and their properties, contributing to the broader understanding of periodic phenomena and the analysis of waves and oscillations, which underpin much of modern physics and engineering. His work here was about building a more robust and analytically tractable framework for understanding angular relationships and their applications. A fascinating intersection of Sylvester's geometric and analytical prowess emerged in his engagement with problems of celestial mechanics, particularly his considerations related to the n-body problem. The n-body problem, which seeks to describe the motion of multiple celestial bodies under mutual gravitational influence, inherently involves complex spatial relationships and trajectories. The challenge of finding general solutions to this problem had occupied mathematicians for centuries. Sylvester's approach, grounded in sophisticated analytical techniques, sought to uncover invariant quantities and fundamental laws governing these intricate dynamical systems. His insights into the stability and behavior of such systems highlighted the profound connections between geometry, calculus, and the physical world. The intricate dance of planets and stars, a problem of immense practical and theoretical import, provided fertile ground for his analytical mind to explore the geometric underpinnings of physical laws. Sylvester's geometrical insights were foundational, resonating with the evolving landscape of mathematics. His efforts to bridge the gap between synthetic and analytical geometry and his contributions to trigonometry laid groundwork for subsequent developments. The analytical tools he forged and the conceptual frameworks he introduced proved instrumental in the later blossoming of fields such as differential geometry and algebraic geometry. These disciplines, which explore the properties of curves, surfaces, and higher dimensional spaces using the powerful machinery of calculus and algebra, owe a significant debt to the foundational work of mathematicians like Sylvester, who championed the integration of these disciplines. His insistence on rigorous analytical methods within geometry provided a crucial stepping stone for mathematicians who would later build upon these ideas to explore increasingly abstract and complex mathematical structures. The enduring relevance of trigonometry in fields ranging from signal processing and computer graphics to quantum mechanics and financial modeling further underscores the lasting impact of his efforts to refine and advance its study. His work ensured that the language of angles and their relationships remained a vital component of the scientific toolkit, adaptable to new challenges and applications. The problems Sylvester addressed were often profound, seeking to imbue geometric and trigonometric studies with a new level of analytical sophistication and structural understanding. His unique solutions frequently involve the introduction of novel notations, the development of specific algebraic techniques applied to geometrical configurations, and the uncovering of deep underlying mathematical relationships. He possessed a remarkable ability to perceive the algebraic essence of geometric forms and to express it with clarity and precision. This approach solved existing problems and opened up entirely new avenues of inquiry, demonstrating the power of a unified mathematical perspective. His intellectual legacy in these areas lies in his persistent quest to reveal the interconnectedness of mathematical disciplines and to forge tools that empower deeper exploration. Sylvester's intellectual journey extended to a profound reimagining of algebra itself, a vision he termed the new algebra. This was a departure from the more utilitarian or calculation-focused approaches that had often prevailed. His aspiration was to forge a more unified and abstract framework for mathematics, one that moved beyond the specific manipulations of numbers and equations to explore the underlying structures and relationships that govern them. Sylvester perceived a deeper coherence in the intellectual landscape of his time and interconnectedness that could be revealed through a more generalized, abstract lens. He sought to develop algebraic tools possessing universal applicability, capable of illuminating problems across geometry, number theory, and analysis. Central to this new algebra was Sylvester's pioneering work with matrices, a concept for which he coined the very name. He recognized that arrays of numbers, arranged in rows and columns, embodied fundamental mathematical operations and relationships. His investigations into the theory of invariance, particularly the study of quantities that remain unchanged under certain transformations, led him directly to the properties of these arrays. The problems of his era included the need for a systematic way to describe and manipulate linear transformations in the algebraic forms that these transformations left invariant. Sylvester's solution was to treat matrices as entities in their own right, subject to their own rules of addition, multiplication, and inversion. He explored their characteristic properties, such as determinants, and began to lay the groundwork for matrix algebra as a distinct and powerful branch of mathematics. This is a significant conceptual leap, moving from viewing matrices as computational aids to understanding them as fundamental objects of algebraic study. The implications were far-reaching, providing a language for concepts that had previously been cumbersome to express. His advocacy for abstraction was a strategic imperative for the advancement of mathematical understanding. Sylvester believed that by focusing on the essential properties and relationships, mathematicians could uncover deeper truths and develop more powerful general theorems. This meant embracing symbolic representation and abstract structures, even when the immediate practical applications were apparent. He saw the potential for these abstract concepts to unify seemingly unrelated areas of mathematics, revealing common underlying principles. This pursuit of generality and structural understanding was a hallmark of his approach, distinguishing his work and influencing the direction of mathematical thought. Sylvester was a profoundly influential educator and mentor. His tenure at Johns Hopkins University, beginning in 1976, marked a pivotal moment for mathematics in America. He arrived at a time when advanced mathematical study was still nascent in the United States, and he immediately set about establishing a rigorous academic environment. He fostered a culture of research, encouraging his students to engage with the frontiers of mathematical knowledge and to contribute their own original work. Sylvester's pedagogical approach was characterized by its intensity, its intellectual rigor, and his own infectious enthusiasm for mathematics. He believed in the power of questioning, of probing assumptions, and of pursuing ideas with relentless determination. His lectures were renowned for their clarity, their intellectual depth, and their ability to inspire. He introduced American students to the latest developments in European mathematics, translating complex ideas into accessible forms while maintaining their essential rigor. He saw teaching as an active collaboration in the discovery of mathematical truth. His seminars and discussions were vibrant intellectual arenas where ideas were debated, refined, and expanded. This direct engagement with students, this fostering of a research community, was a crucial element of his legacy. He cultivated mathematicians. The impact of his time at Johns Hopkins was transformative. He attracted talented students and colleagues, creating a dynamic hub for mathematical activity. Joseph Sylvester's intellectual architecture, erected through decades of relentless inquiry, continues to shape the very landscape of modern mathematical understanding. His contributions, extending far beyond the resolution of specific problems, represent a profound reimagining of mathematical language and a visionary expansion of its conceptual horizons. The abstract algebraic structures he championed, the elegant notations he introduced, and the analytical tools he forged have become indispensable elements in the mathematician's arsenal, permeating diverse fields from the theoretical underpinnings of quantum mechanics to the intricate algorithms driving contemporary computer science. Sylvester's enduring legacy resides in his capacity to perceive the underlying unity within seemingly disparate mathematical phenomena. His pioneering work in invariant theory, for instance, provided a powerful framework for understanding how certain mathematical quantities remain unchanged under transformations. Many of his students went on to become leading mathematicians in their own right, carrying forward his intellectual traditions and contributing significantly to the growth of mathematics in America and beyond. His influence extended to the very structure of academic mathematical life, shaping the expectations for graduate education and research. He demonstrated that rigorous, abstract mathematical inquiry could flourish in the United States, laying essential groundwork for the nation's future scientific and technological advancements. The new algebra he championed, with its emphasis on matrices and abstract structures, has become a cornerstone of modern mathematics. Matrix theory, which he named and helped to establish, is now indispensable across virtually every field of scientific endeavor, from the analysis of quantum mechanics and the algorithms that power modern computing to the modeling of complex systems in economics and biology. The concepts he introduced are fundamental. His vision of algebra as a study of abstract structures and relationships continues to guide mathematical research, providing a powerful language for understanding the universe. Sylvester's commitment to abstract thought, coupled with his exceptional ability to translate these abstract ideas into tangible mathematical tools, has left an indelible mark on the intellectual landscape. He fundamentally altered the way mathematicians approach inquiry, shaping the very foundations upon which future discoveries would be built. His efforts in popularizing abstract algebra and his pedagogical impact ensured that his vision would resonate and grow, influencing generations of mathematicians and scientists who followed. His work provided a more elegant and powerful means of expressing complex mathematical ideas, unifying disparate areas, and revealing deeper truths about the nature of mathematical relationships. This concept, initially developed to analyze algebraic forms, proved to be a fundamental insight with far-reaching implications. The methods and perspectives he cultivated in this area offered a new lens through which to view symmetry and structure, principles that are central to many branches of physics, particularly in the study of symmetries and physical laws. The mathematical objects he studied and the sophisticated techniques he employed to dissect their properties laid essential groundwork for later developments in differential geometry and topology, fields that describe the curvature of space-time and the fundamental properties of shapes. His profound engagement with number theory, particularly his work on Diophantine equations and partitions, offered elegant solutions to ancient problems while simultaneously opening up new avenues of research. Sylvester's identity concerning the number of partitions of an integer into distinct parts, and his exploration of the Frobisher's coin problem exemplify his ability to distill complex combinatorial challenges into tractable forms. These investigations, while rooted in the abstract beauty of number theory, possess a surprising resonance with practical applications in areas such as cryptography and the optimization of resource allocation, where understanding combinations and constraints is paramount. The very notion of a partition, the breaking down of the whole into its constituent parts, is a concept that echoes across scientific disciplines, from the analysis of molecular structures to the study of population dynamics. Furthermore, Sylvester's introduction and championing of matrix theory provided a powerful new algebraic language for representing and manipulating systems of linear equations. His insistence on the importance of matrices as mathematical entities in their own right, rather than mere arrays of numbers, was a crucial step in the development of linear algebra. This development offered a compact and efficient means to describe complex relationships and transformations, proving invaluable in fields such as engineering, economics, and the burgeoning discipline of data analysis. The ability to represent and operate on vectors and transformations using matrices has become foundational to fields like computer graphics, machine learning, and the simulation of physical systems. The very concept of a matrix, a structured arrangement of elements, mirrors the organized nature of data encountered in countless scientific endeavors. His vision for new algebra, a discipline focused on the study of abstract operations and structures, fundamentally altered the trajectory of mathematical thought. Sylvester was a fervent advocate for abstraction, recognizing its power to unify diverse mathematical concepts and to reveal deeper, more fundamental truths. He understood that mathematical progress often hinges on the development of new conceptual frameworks and the refinement of the language used to express mathematical ideas. His pedagogical efforts, through his prolific writings and his influential teaching positions, were instrumental in disseminating this forward-looking perspective, inspiring a generation of mathematicians to embrace the power of abstract reasoning. He fostered an environment where intellectual curiosity was paramount, encouraging exploration and the pursuit of elegant solutions. The impact of Sylvester's work extends into the modern era, influencing areas that were nascent or unimagined during his lifetime. The analytical tools he developed for the study of invariants find echoes in the search for fundamental constants in physics and in the algorithms used to identify patterns in vast datasets. His insights into combinatorics and number theory continue to inform the design of secure communication systems and the efficient organization of information. The abstract algebraic structures he explored are now cornerstones of theoretical computer science, underpinning the design of programming languages and the analysis of algorithms. Sylvester's life was a testament to the power of intellectual perseverance. He navigated societal prejudices and personal challenges with an unwavering dedication to his mathematical pursuits. His ability to synthesize complex ideas, to forge new conceptual pathways, and to articulate his discoveries with clarity and elegance has left an indelible mark on the scientific enterprise. He reshaped the very tools and language with which mathematicians approach inquiry, providing a more powerful and expansive framework for understanding the universe. His legacy is woven into the fabric of mathematical thought itself, a testament to a mind that saw the profound beauty and practical power of abstract reasoning, forever enriching the intellectual heritage of humankind.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.